Aime Lay-Ekuakille from the University of Salento in Italy, as you mentioned before. The title of my presentation is The Advanced Transforms for Engineering, with the subtitle, How to Solve Ill-Posed Problems and Applications. This topic is a key topic for me, for my career, because it embraces different aspects connected to physics, chemistry, electrical and electronic engineering. I will show you, thanks to this content, the statement of the problem, how it is possible to use the advanced transform, and the main motivations of this type of research, and what are the ill-posed problems impact to the nowadays problems. I will introduce you some formalism about the filter diagonalization method and decimated signal diagonalization, which are the two specific subtopics I would like to present to the audience. And I prepared 4 applications, one for leak detection in pipelines, I mean in urban waterworks, which is a key problem due to the huge amount of leakage in urban waterworks. And the second application will deal with the how it is possible to detect fault in specific tools in mechanical diagnosis. And I will show you the application, the use of FDM in order to discriminate odors using any nose we fabricated. And the last application will deal with the epilepsy, so to neuroscience. But I will speak more about the leak detection in the pipelines, and I will trace out conclusions and show you some further readings. So as I told you before, there are connections between some problems, even if in the field of engineering, but connected to decaying processes. We use them in biomedical instrumentation, biomedical physics, such as in functional nuclear magnetic resonance, in detecting how it is possible to bring together vegetables, plants, in order to give them properties of resisting to external agents. And it is also possible to explain industrial process using radioactivities. So the problem is, what is the distribution? So all these issues are connected to Poissonian distribution. So there is a decaying process we have to face. It is a challenge. So in spectral analysis, we we are motivated to use Fourier transform or Laplace one, but due to the limitations of both transforms in some specific fields, at the beginning of years 19 of the last century, some people working in the field of physics and chemistry decided to investigate deeply in order to understand some mechanism related to the decaying vibrations. So they started working to new methods, namely filter diagonalization method and decimated signal diagonalization. But they are also both approaches also correlated to one other, such as DPA or PDA, Pade decimation approach. So the idea is, given a specific phenomenon we want to study, it is possible, if we understand the true reason of this phenomenon, it is possible to reconduct this aspect to a summation of different signals, as you can see here, and we must be able to understand if these phenomena are linear or nonlinear. So if we are able to express them in this way, we will be able, in the field of physics and chemistry, to find two things: the amplitude of the signal representing this phenomenon and the frequency related to the vibration. So in this way, we will be able to carry out something different with respect to FFT. So we find some specific obstacles. These obstacles are connected to the way we start to process this signal. So we generally meet difficulties in making the inversion of this kind of signal represented in terms of matrices. So the idea is, in this case, I use PNT representing, for instance, the pressure in a pipe connected to this autocorrelation function. So the limitation of using the matricial function and making the inversion is very, very difficult, because we have to calculate, we have to compute the eigenvalues omega k, so that a specific matrix should be diagonalized. This is the problem. So we decided in our approach to generalize this problem of calculating the eigenvalues. This is called the generalized eigenvalues issue, faced in in geometry, in calculus, and algebra. In this way, we are able to find the frequencies and the amplitude. But it is not easy when we have a huge number of data. So we have to introduce some algorithms allowing to find the solution. Basically speaking, the eigenvalues, which are the solution of this problem, are all included in this circle with the radius equal to 1. If the solutions, mathematically speaking, in terms of eigenvalues are included in this circle, so the problem is correctly solved. But generally, it is not easy. So we have to use the single value decomposition, also called more Penrose pseudo inverse, and we can use another version called smoothed least squares. But generally, people working in this field use the Tikhonov algorithm for regularization. But more detail about this formalism are included in the next section. This is an example of what if you have the signal aforementioned, you have to find the eigenvalues. More details are included in this paper. So this is the formalism of FDM and DSD. Maybe it could be very heavy to understand. It is how it is possible, it illustrates how it is possible to write a specific algebra of this summation of damped sinusoids included in this signal to be converted in something very, very clear. So I will try to skip this formalism and show you when we have the result, what is the difference in terms of frequency and amplitude if we want to make a comparison between Fourier transform and FDM. So for different frequencies, we can understand that at the beginning it seems there is no difference between FFT and FDM. Surely there is a difference. The difference, as we will see further, is in terms of the peaks. So in terms of resolution. This is a summary of the FDM flowchart algorithm, where we have to calculate to build the spectrum, included the amplitude and the frequency. The second algorithm as advanced transform is the DSD. The DSD is based on the FDM. What is the difference with the FFT and what is the difference with the FDM? In FFT, in Fourier transform, we have difficult to make the windowing. So intrinsically speaking, FFT exhibits some limitation in order to see the difference between waves. But in a DSD, we are able to distinguish, to discriminate by means of different windows, the quality of the spectrum. So as we have done in FDM, here we are also interested in calculating the frequency and the amplitude. So we can see here the DSD flow chart. As I told you, it also uses the FDM as basis, So the clear difference between DSD and FFT and FDM FFT is in the resolution. This is given a signal with maybe included in a decaying process. Here we have the magnitude in terms of FFT. So if we come here in DSD magnitude and DSD absorption, we are able to discriminate two peaks, while in FFT we are not. So this is a crucial issue because distinguishing the peaks, we are able to recover crucial information included in the spectrum, or maybe in the spectra. So in FFT, there is a loss of information. In DSD as well, in FDM, there is a gain of information. Okay, so this is the first application. The first application is in the field of leak detection in pipeline. There are different reasons for which we get leaks in water works in cities. Maybe the quality of the material we are using, maybe the excessive pressure of water, or in general of fluids, and corrosion, and other issues. Okay, so there are basically two main approaches in detecting water loss. So we can work in the field of physical loss, real loss. We can improve the quality of pipe breaks, and maybe we have to reduce the storage overflow and old house connection. Okay, but the company working in this field can also face the problem in the so that they can recover, they can retrieve the so-called apparent loss. I mean, maybe uncertainty in measuring, the quantity of water. It could be also possible some cities, the water, we have the issue related to water depths, and billing, maybe billing anomalies. So here we can see in the water leakage in Europe, and we can start from I mean 10%, which is normal physiologic, to 50%. We have here one case, I think, in Ireland and Poland. So in general, in Europe, in the Western countries, we have a loss of more or less 650 million dollars per year. So we have to manage this issue. We have different techniques to do so. So you can see here the idea of retrieving, improving the quality of pipes, and the pipes are strategic infrastructures, so they are a basic issue. So we have two broad separations in terms of facing this issue. So we have the hardware-based methods where we can use acoustic waves in order to see within and outside the pipe what happens. We can include a cable sensor close to the pipe, along the pipe. We can use the fiber optic. We can also detect soil monitoring. Maybe we want to understand the amount of moisture in the soil. And we can also use the ultrasound. And the last technique could be the vapor monitoring. As a counter approach, there is the software-based methods. So we have to use to make calculations based on a sensor put on the pipeline. We prefer, my group and I, we prefer to use the pressure point analysis instead of the hydraulic approach. So in the pressure point analysis, we put a sensor in a pipe. In the interim, I can show you these are the configurations of the hardware-based methods. So we can use the time domain reflectometry. This is the pipe. We launch a signal, and there is a return wire along this pipe to give us if there is a break in the pipe. So we have this. Another one is, as I told you before, the acoustic emission sensing. This is a passive and active. Passive because we have to launch a wave, active because we have to launch a wave, and passive we get a result after some modifications in the pipeline. So we can also use laser Doppler vibrometer. This is also our expertise. In this case, we have like a laser here targeting the pipe, and we can understand the variation of the pressure within the pipe and say if it's okay or not after a classification based on wavelength. So we have to remove noise from the pipeline. And this is also our work, so we can use the imaging. We need a pipe with a possibility with the emitter here, and we have a camera, and after different rotations, and we are able to understand, to read and to connect the rotations and the velocity to the geometrical figure to be detected. In this case, we can understand the flow within the pipe, but we can only see the pressure, the flow, its velocity, but not directly the leakage. So in the spectral analysis, which is the key issue of this, one of the key issue of this talk, we have the normally we have a pipe in normal situation. This is the flow direction. In case of a break and leaks, we have the return, the negative pressures going against the flow direction. So normally, this changes creates a vibration within the pipe. Okay, so the idea is to make a comparison between the normal flow direction, the normal amount of the flow within the pipe, and this disturbance and this variation, a sudden variation of the pressure within the pipe. So you can see here, this is a theoretical spectrum. We expect. This is the measured spectrum, so detected by a sensor 1, and we make a comparison. We make the comparison between both signature, the original we expected or we expect, and what we have detected by means of the pressure sensor put in on the pipe. So if you look at here, there is a difference. This difference is the indication of leak, sudden variation of the pressure. So this is the mechanism of the pressure detection. We have here the normal flow. This is the leakage. This is the negative pressure, and we have a vibration of water molecules displacement within the pipe. So we can say that if we deal with the FDM, if we deal with DSD, if we deal with the DLP, with the PDA, and so on, this kind of advanced transforms, we have to face the problem as the experts are doing in the decay process in radioactivity. So one of the idea is to use these transforms by leveraging the water molecules in a relaxation process. This is an example, the dynamics of radioactive decay process, and we have the beta decay process by means of Betz 5 Sekar mass formula. So we can make a further comparison. When we decided to, especially when I decided in 2007, I decided to work in this topic. I made a comparison between the blood hydrology, so the displacement of blood within the human veins and arteries, and the thrombosis could be compared to the leakage in a pipe. In the human body, we have vessels, we have veins, we have arteries, So they are similar to pipes in the normal situation. So from the idea of people working in the field of nuclear resonance, we decided to take what is useful for us in order to make a transportation to the field of leak detection. So this is a practical use of the FDM. This is, for instance, a sensor on a normal pipe. Here you can see an antenna allowing to transmit data from these sensors, pressure sensors, to I don't know, to a mobile phone, to a point where the companies working on the maintenance of the waterworks can receive data. Here in one of our labs in Lecce, this is a pressure sensor mounted on the pipe. This is a pump simulating the different pressure we can get in the pipeline. So this is one of the a small part of the pipeline in the lab. You can see here that we have a difference between, for instance, FFT here, the uncertainty on a pipe of 70 meters. We have an uncertainty with a linear regression of more or less 8 meters, while with the FDM, we have less than 1 meter. So every 1 meter of FDM uncertainty, we have 8 meter of FFT uncertainty. So this is very, very clear. As I told you before, it is a question of resolution. We make also a comparison with the decimated signal diagonalization. The results of DSD, we can see also that in some cases they are close to FDM, and this is a further algorithm based on DPA we used in the leak detection. So another example, just a few slides to conclude, is in the field of fault detection. We can detect faults in materials where in mechanical activities. So here you can see a classical, a traditional EMD, empirical mode detection, decomposition, and where we can see the problems in the wear. And here, the application of FDM. FDM is very, very simple because it displays. Here we have no wear, medium wear, and severe wear. And a further application of advanced and transform is in the field of food characterization. So we are able with the eNose to detect the presence of materials, bad materials or other components in a food. This is an example of acetone where we have different tests thanks to FDM. And the last example is in the field of biomedical application. Here, we want to detect in a multidimensional way the presence of epilepsy in a child. So here we have the abnormal EEG with the peaks. Look at here, it is 10 to 5, and here we have a normal EEG. It is 6 10 to 4, one order of a difference. So in the previous case, we got the result of a peak in the system. So what to say as conclusions? I think that the advanced transforms are very important in the field of engineering in many fields. As I told you, in the field of electrical, electronic, chemistry, physics, but they can also allow to modify, to improve the fabrications of sensors. So some references, and thank you so much for your attention. I beg your pardon for, for being very long in this presentation. Okay.